around 14% slope there, 14 degree slope, sorry, there, and that would really just hinder construction to that site. There would potentially need to be some
like a different access road.
Right, a different access road to the actual site in order to build it, which does make construction of it a little more complicated than the solar option for sure. Yeah.
That was actually my question.
Okay.
Yeah. The proposed location is actually on like a flat surface. It's just getting there is like a very steep.
Should be pointed out too that is an example photograph. That's a foundation for utility scale wind turbine.
Yeah.
So the foundation would not be anywhere near that expansive.
Would you have any worries about, because it's right next to the playground, would you have any worries about like children running around by the bottom of it or any safety problems with that?
Yeah, that is a concern for us. And we'll talk about it later too, but this site was actually chosen because it does meet that setback requirement still, so it should be safe given the setback requirements, but there's definitely concern with it being very close to the playground. Yeah.
So, if you're gonna, do you think you'd be able to like accomplish building this in the summer over 3 months? Because if not, you would have to build it with like the kids actually outside in the construction zone. So how would that work?
You'd have to be inside recess.
Yeah, smaller recess area.
Yeah, I don't think. Well, if construction were to go longer than the summer months, that whole area would have to be properly blocked off for the duration of construction, unfortunately, but
I wouldn't foresee construction lasting
But,
longer
yeah.
than 3 months or something. We don't have like that, it's not that large of a scale of a wind turbine, so.
yeah.
Were you worried at all about it being like an eyesore to the highway or anything like that?
Yeah, definitely. We'll actually have a photo a
You can
little
see it
later on
from the
that'll
highway.
show you what it would potentially look like at Juda School if it were to implement it there. So we'll definitely put that out to you.
Yeah, so after we go through each of the 3 design options, we're gonna go through sort of like how we considered which one we plan on recommending to you guys. It's going through a decision matrix, and we took into consideration things like safety and also like visual obstruction and disruption. So that's definitely something we'll touch on a little bit later.
Yeah.
Is this really the minimum height tower that you could use? I mean, you said 37 meters for the tower.
Yeah.
Does the payback, that's like 200 feet, correct, roughly?
Yeah.
So, did you consider like a 120-foot tower, or
Yeah, so you had given us that wind assessment report, and
Yes.
those towers were about that height. You're talking about that 120 feet range.
Mhm.
They just weren't generating enough
Okay.
energy at that height. So this wind assessment also told us at 60 meters could achieve 13 mile per hour winds. So we wanted a higher tower to take advantage of those.
So really, you had to get up higher to get into that
Yep.
payback range.
Right.
Okay.
The site that we looked at, that I talked about, the Wausau East High School, they use this specific turbine. So
Yep.
a lot of the schools that I think have implemented these wind turbines have used this specific model.
Okay. All right.
Okay, so I'm going to give it off to Morgan, who's going to discuss our third and final option. So our third option consists of a geothermal system paired with the same solar array outlined in option 1. So since the technical aspects of the solar array have already been discussed, I'll be focusing on the geothermal component. So the first step to designing a geothermal system is to determine the necessary size of your system. This is often done using an advanced software such as BLAST, which requires inputs for thermal resistance of exterior windows, walls, and doors, and also thermal loads of each room within the building. However, due to our time constraints, Professor Tincham, who was also helping with the geothermal component of this project, did not believe that it was feasible for us to gather all the necessary information to use a complicated software like this one. So instead, he recommended that we design our system based on the peak month of natural gas usage. So after plotting Juda's natural gas usage, this was determined to be January of 2016. So if you design your geothermal system around the peak month, it can be assumed that that system would also cover the natural gas usage in the other months as well. This means that we assumed that a properly sized geothermal system would offset 100% of your natural gas costs. However, this does not account for inefficiencies in the system because those could not yet be identified and quantified. So if this option were to be chosen, we would consult with a professional geothermal installation company, which would help us better understand what those inefficiencies are in the system. So option 3, with the geothermal system paired with the solar array, would offset about 66% of Juda's total annual energy costs. So the next step is to design a source loop at Juda School. This is done by taking that peak month of natural gas usage and converting it to a number of tons. So for Juda School, you would need a 92-ton system. A good rule of thumb in a heating-dominated climate like southern Wisconsin is that you'll need 200 feet of bore per ton. So this means that Juda School will need about 18,400 feet of bore. We are proposing to place the source loop underneath the outfield of the existing baseball diamond on the west side of the school. And a horizontal loop was considered, but there's not enough available space on the school property to support such a large system. Therefore, BECO is instead recommending a grid system of 92 vertical wells, each 200 feet deep, as seen here. The next step to designing a geothermal system is to retrofit the existing heating distribution within the school. So BECO met with Phil Trotter, the maintenance supervisor, to help us better understand your current heating system. So each section of the building on this floor plan outlined in a different color represents an area that is serviced by its own air handling unit. These air handling units are currently getting hot water from the boilers located in the basement, and there's also already installed hydronic heating coils in most of the classrooms throughout the building. This means that BECO will be able to replace the boilers in the basement with water-to-water heat pumps, which will send the hot water throughout the school and heat the rooms that way. The elementary area outlined in red on this diagram is slightly different because that area, each classroom has its own individual heat pump located outside of the room. So those will need to be replaced with water-to-air heat pumps, which will actually allow for more climate control in those classrooms. The offices outlined in black are also slightly different because while they do have their own air handling unit, there are no hydronic heating coils already present. And so water-to-air heat pump would need to be installed in this area as well. Overall, BECO feels that we can make use of Juda's current distribution system so that no new piping or ductwork needs to be installed. This will help keep initial costs down. If this option were to be selected, a full soil analysis would need to be completed. BECO used a paper written by Lauren Meyer and signed by Professor Tinjum, which tested the thermal conductivities of common Wisconsin rocks, including sandstones. We used this to estimate the thermal conductivity of the St. Peter sandstone located at Juda School. But if a geothermal system were to be built, an in-situ thermal conductivity test would be recommended just to verify these assumed values. So, does anybody have any questions about the proposed geothermal system? Yeah.
If you were to do the horizontal coils instead of the vertical, how big of an area do you think you would have needed compared to what we have? So
I can't remember the exact number, but you would have had to use your entire baseball diamond. So instead of just the outfield, we would have had to dig up the whole baseball diamond and then even extra area outside of that, which ran out of school property. So not gonna work.
Well, and piggybacking, I got a question about that. Is how big a horizontal system could we fit? I mean, because again, you're talking about whole system, but if you wanted a horizontal system, could that do a couple zones, or is there a partial answer to this?
So you'd have to size your system down, and we didn't try to do that just because it makes it more complicated to try to figure out how much energy we would be creating, because we designed the system around the peak month instead of the other way around. So if we had access to a more complicated software where we could put in the size of system we want, then we could figure out how much energy it would produce. but we just didn't have access to that due to our time constraints.
Sure.
And so we didn't do any partial
Okay.
systems, we just went for the whole thing.
Also, I think there are some cost savings if you already have like the drilling
Yeah.
like equipment out there.
Right.
Like the bigger system you do, the more like
Yeah, it's
return you'll
expensive,
get.
yeah, it's
Economy of
expensive to
scale.
get those drill rigs out there, so if they're out there,
And you mentioned there were 92 wells in the field.
Yes.
Are there tops on those then, or are those all underground?
they're all underground. So once it's all installed, you wouldn't see anything or even know it was there.
If you, we could go back later, but if you look at the, we have a picture of Madison West High School, and their geothermal field is under their football field. So
Yeah.
they're playing
All
football on that
underground.
field, and you
Okay.
can't see it at all. You would have no idea it was there.
And that's the other, just to note on the geothermal, or the horizontal versus vertical, a lot of schools we found actually did opt for more of the vertical wells. Because horizontal wells are enough space for residential properties with big lawns, but for schools with such high natural gas consumption, it's just, you don't have enough property for how much you're consuming.
And I don't want this to come out the wrong way, but is it safe to say on a system like this, it's go big or go home? You don't, that you're going to either go for the whole school or not go at all? Is that not a safe assumption?
It could be sized down. We just don't know how like payback period is affected by
Sure.
that. Like if the initial installation of the system is too expensive,
Right.
it would just give you a much longer payback period. So that's why we didn't do any sizing down of it. But it would definitely be possible to look into later on.
Sure.
Maybe if we wanted to.
Okay.
For those of us that maybe aren't as familiar with geothermal, can you just explain exactly what that means?
Yeah, so there are, so basically once you get to a certain depth below ground level, the temperature of the earth will be the same. And in this area, it'll be 50 degrees. So once you get below like 20 feet, the ground actually stays warm. So even in the winter when it snows, the ground is still pretty warm. And you're basically using the ground as a heat source or heat sink. So the pipes will have a solution going through them. It's usually water and then maybe a little bit of a certain chemical. And so it will pick up the heat from the ground in the winter. It'll pick up the heat from the ground, bring that back into the school. And then the heat pumps within the school will turn that into hot water or hot air in order to heat throughout the building. So those hydronic heating coils I was talking about act sort of as a radiator, so you're sending that hot water to them and then they'll spread the heat throughout the classroom. And then it works in the opposite way during the summer. So it uses the ground as a heat sink. So the warmer water will come back in and distribute that there and then come back colder. So it acts as a either source of heat or sink is how that works.
Very well said.
Okay. Yeah.
And if it's designed around the gas, do you expect electrical savings on the air conditioning side in the summertime?
Yeah, so that's something that we didn't take into account in our preliminary design. It's just because we weren't sure how much you guys were spending only on AC, because we just got electricity as a total.
Right.
But after looking into it a little more, we found that schools generally use about 35% of their electricity costs is spent on AC. And so this could actually supplement that as well. So all of the energy savings of this are actually an underestimation, because we would select heat pumps that have, it's called a reversal valve, and so they could be turned around so it could also be used to air condition. So not only to heat, and so it would also have energy savings on electricity that we didn't even include in this. Yeah.
So in months where like the natural gas use isn't as high, could we adjust how much heat we bring out from the geothermal system to try and like save money, or is that?
I would say once you have your system installed, there's not really any like maintenance cost to the system. So it's not something where you're like taking something out of the ground and like using it. It's more just something that's kind of continually circulating. So you just have to build it for a certain size that you would anticipate. And
Yeah, you can't really control it that way. It's more like once you build it, that's how much it's bringing in. I mean, obviously you can control the temperature in each classroom,
Yeah.
but it wouldn't be something you can like turn down necessarily, I don't think. Does that make sense?
So what would happen if we exceeded like that peak amount of, would we just have to like revert to using natural gas for that amount of time or something?
I think so, yeah. If designed properly, you should never exceed the peak amount. That's how they're designed to be that way, and so that's why you can even get rid of the boilers, because you don't need them anymore. And obviously a professional geothermal installation company would know more of an exact analysis, probably using a more complicated software. We designed this around rules of thumb that you can find just by doing research online. But actual geothermal installation company would have a software that could design the system very specifically for the school. So.
This one is in conjunction with the solar also?
Yeah,
it's both, right?
Yeah, it's
Just
both,
by
yeah.
itself.
So they're not tied in any way.
Right.
It's just that we're using both at the same time, so that's how you're getting so much savings in energy, because the solar is also offsetting electricity at the same time. Yeah.
Did you do any analysis on just what geothermal would save?
So we did, yeah, and the reason we decided to pair it with the solar array is that it didn't quite meet that 25% goal, and the solar array actually helps to decrease the payback period on it, doing it at the same time. So that's why I decided to pair them together. Yeah.
So of the three options that we discussed, which one has the shortest payback time?
So we're actually going to go over that in just a second. So now we're going to get into the economics and environmental analysis, safety, constructibility. So we'll show you all those values in just a couple slides. Okay? All right. Good. So now we'll move into the comparison of the alternatives and also show you guys our decision matrix and how we created that. So the environmental analysis consists of the lifetime of the system, the CO2 avoided over its lifetime, and also the amount of money saved in energy costs per year. The geothermal system has the longest lifetime because the source loops are warranted for 50 years or more. The solar array has a lifetime of about 30 years, and the wind turbine is at 20 years. So option 3 also had the highest CO2 avoided over its lifetime and the highest energy savings per year, just because it combines both natural gas savings and electricity savings. And the option 2 of the wind turbine was the least desirable in all 3 categories. So this shows our decision matrix. The environmental analysis was given the biggest weight at 30%, because the main goal of this project was to design a reliable, renewable energy system that would help Juda School decrease its carbon footprint. All 3 separate subjects within environmental analysis were given the same weight, and as discussed before, option 3 scored the best in all 3 categories, while option 2 was the least desirable. So now I'll hand it over to Emma to talk about the safety of each alternative. So as we were designing these systems for you guys, the safety of both the students and the teachers is a high priority for us. So we analyzed each option thoroughly to understand these risks associated with them. So for option 1, the solar panels, the largest risk with this is the high voltages that will be produced. Though if installed correctly, these risks will be minimal. Option 2, the wind turbine, has the most safety concerns, just because during the winter, icing can occur, which you can see up here. That's when ice forms on the blades and could potentially fall off and harm someone. Also, maintenance on wind turbine, as you're 37 meters in the air, the worker does have to be harnessed in, which does which is like a fall concern. And then finally, there are high voltages also associated with this wind turbine. Option 3, the geothermal and solar system combination, actually does have the potential to increase the safety here at Juda School, as the boilers in your basement would be replaced with the water-to-water heat pumps, and boilers do have a very small potential to explode. So in that way, the safety of the school would actually be increased. So this is the safety analysis within our decision matrix. Safety is a high priority, as I stated previously, so we gave it a weight of 25%. Option 3, as it does have the potential to score, and option 2 because it does have a lot of high risks associated with it was given the lowest score in this decision matrix. I'd like to hand it off to Robin to discuss constructability.
Awesome, thank you. So constructability of design option 1 is the most straightforward, as there is ample available roof space as well as few obstructions. However, one obstruction that does need to be taken into account is the gas line seen here on roof section A. This gas line will need to be moved almost 5 meters to the center of that roof to the proposed walkway, just so that our solar arrays can be in continuous strings and have more space for these as well. As well, the roof section B will need to be repaired, like I had said before we implement the solar arrays on that roof section. This is because once you put the solar arrays on that section, it can be really costly as well as risky to remove those so that the roof section can be replaced. So this roof section we recommend should be replaced with the TPO, which is seen here on roof section A, which is a great material as we had talked about before. So the constructability of the wind turbine is far more complex.